Welcome to the Berkeley Seminar. Hello Chris. Today we're delighted to have Sam Vandervelde, who I met in 2015 when I was a counselor at a math summer camp called Math Path for middle schoolers. And Sam has the incredible ability to keep 100 middle schoolers at the edge of their seat with fascinating math tales, so I'm sure he'll have no trouble with us. Currently, he's also the head of Proof School, and so we've already chatted a bit about that. And today he's going to tell us about where is the middle of a Fibonacci sequence. Great, take it away, Sam.
Thank you, Sophie. So I'm going to give us all permission to sort of unleash our inner middle schooler. As I was mentioning earlier, I do straddle these two worlds where I've been in academia for a good chunk of my life. I spent 8 years at St. Lawrence University as a math professor, doing all the things that one does as a mathematician, and loved every aspect of that. It was a great experience, except there were no kids in my life, and so to fill that void, I would go every summer. I would spend 2 or sometimes even 4 full weeks at Math Path, this program where I met Sophie, for sort of 11 to 14-year-olds who love math, and much of the culture that I encountered there, and this sort of like amazing, just this transformative experience for kids, being for the first time, many of them in the company of lots of other kids who were wired the same way they were, was informed a lot of what's happened at Proof School since then. So I learned during those years how to take a mathematically sophisticated topic and make it accessible and exciting for kids with a solid mathematical background, but still kids, like 11 through 14-year-olds. So it was this very interesting and maybe unusual exercise that I was engaged in. So we're going to just embrace it here this morning. There's some really interesting mathematics to be discovered here. I am positive that you will all enjoy where this goes. But at the same time, it's aimed at 11 to 14-year-olds, and I feel like this would be a worthwhile little thought exercise, because part of what we do, I think, as communicators of mathematics is connect with audiences that don't necessarily move through material in the same way or at the same pace as we do, and having to, like, if you can present something, it's this adage, right? If you can present something to a middle schooler, then you really understand it, or I'll leave it to you to judge how worthwhile this is. But here we go. You can pass notes and like make jokes and talk, and there's gonna be a lot of interaction. So you've been warned. At any rate, and I'll be doing the same kind of via the slides. So don't be too taken aback if we like descend to childish humor here. So we're gonna ask this question and answer it. How do we find the middle of a Fibonacci sequence? But just to review, we're going to hold up some fingers. How many terms to get a Fibonacci sequence going? That would be 2. Very good. So let's take these 2. The next one would be 9. Yes, and then need to hear some new voices. 16. Yay. And then you're all doing well adding here before lunch. And then it keeps going. But actually, you can go in the other direction as well. What would be the term before this to make the Fibonacci relationship continue? We'd need a 5, and then we would need, right, so we hit some negatives, and then before that is 8, very good, and it would keep going, right, there'd be a negative 11 in the spot before that, and on backwards. Okay, let's have some fun. I'd like some proposals for which number should be considered the middle of this Fibonacci sequence, and maybe why it recommends itself to you. We're looking for at least 3. This is a group effort. You're going to try to come up with 3 different proposals, and with some sort of rationale that's reasonable-ish. So let's hear a proposal. So here we go. Oh, interesting. So there's sort of a, how do you know where to start that? Okay, so you go to the middle, and then you like, but yeah, some sort of averaging process that as you take more and more, I'm not managing to get, as you take more and more of the, let's try this. I'm looking for laser action. Maybe later I'll pull up my big green laser pointer. That will be exciting, but we'll save it for partway through. And that will lead us to the middle. Another idea.
The first negative number or the rightmost negative number?
So at some point we switch from having alternating positive negative, like and perhaps the spot after that. So you're proposing the number
-3 or 5 in this one.
So either like maybe -3 or 5, depending on whether we go with the last negative number or the first number that's strictly positive. That's our signal that it's time to move along. But here, let's get one more.
2 maybe.
We're going 2 because.
It's going up from there to the right. From that
Oh,
point on.
good. So it's like the sequence is monotonically increasing from 2 onward, and so there's a good candidate. And these are very reasonable suggestions, which makes us like wonder what's going on and like how there's. So let's lay a little groundwork. We'll zip along, but still, yes or no? Just give me thumbs up or thumbs down. Looking for a vote from the audience. Is it Fibonacci? Do every 2 numbers add to the third? It looks like consensus is thumbs up, and you're correct. How about this one? I'm getting, again, mainly thumbs up. So survey says yes. Got a third one here. Actually got 4 of them total for you. Getting, making people think a little bit. Getting a real mixed review on this one.
At some point it should switch to no.
It looks, okay, well here would be an easy way. Someone that said no, which terms are you arguing? So, oh, look right here, -1 plus 15. So I tried to pull a fast one on you, and you didn't let that slip by. Well spotted. This one is, so yeah, technically yes, but this is the one Fibonacci sequence of integers that will that we won't include in our considerations. So good, we've got Fibonacci sequences. Next up. Just to practice this idea, if I've got a sequence of numbers that satisfy the Fibonacci recursion, then I can use them to create new sequences. I could add 1 to every term. Is the result a new Fibonacci sequence? No. Getting a lot of no, and that's correct. The sum of 2 of them doesn't give the third number, so no. How about this? Tack a 0 onto the end of every number. Yes, brilliant. Square every number. We're through like, that can't possibly work. No, like, well, let's move on. Here's maybe the one that will force you to at least think a tiny bit. Yes or no? What if you subtract? If you add 2 of them, do you get the third? And you do. G2 plus G3 does give G4, and then G1 plus G2 does give G3.
You can just add 2 such things.
That's right. Any linear combination of 2 Fibonacci sequences will again be Fibonacci.
Maybe 1, right?
Yes. So that's it. Good. All of this just laying some groundwork. We want to get nice and comfy with general Fibonacci sequences, not just the Fibonacci sequence. So great. And now I have to start to convince us that we can have a doubly infinite sequence and somehow make sense of a middle term when it's like there must be some feature. So here's a sequence that I've made up. It has lots of decimals, which is off-putting, but you can spot the pattern. And while you're doing that, I'm going to grab this. So what is the pattern and what is the next number? Puzzles. Puzzles are a great, like I'm a big fan of puzzles. It's just how I get kids excited about math. All right, what's the pattern and what's the next number?
Should be 35 and a half, I think.
Oh, good. We've got. Is this going to reflect? Hang on, we're going to test it. It does reflect a little. Well, we'll be all right. 35 and a half. And where did that come from?
Power of 2.
Yeah. So I see a 4. That's a power of 2. So you right. The differences between successive terms is, well, here it's 8, there it's 4, 2, 1, half, a fourth, an eighth. Sure enough. So maybe this isn't an absurd thing to ask. Where's the middle of that sequence? Proposals? So right, when you say 1, of course you mean the pair of numbers that differ by 1. That somehow 1 is the middle of the sequence of powers of 2, 2 to the 0, and hence, so either 4.5 or 5.5. I'm not sure which. It's kind of up to you, or up to the mathematician to decide. But sure. So it's going to be this kind of idea that's going to allow us to get our hands on a middle term. But it's considerably more subtle than just this. So let's see what we know about. There's a lot to know about Fibonacci numbers. So we'll just take a few of your favorites. It's getting the lay of the land. Where are we coming from as an audience? So pick one or two. Let's see if we can get 3 nice Fibonacci facts. Here's a nice Fibonacci fact.
A 4x4 matrix that if you keep squaring it, it's the Fibonacci numbers.
When you say 4, do you mean a matrix with 4 entries?
Yeah, I think it's 1, 1, 0, 1.
Right. So this matrix that, yes, and you can use this actually, as I've heard, you can use this to calculate. It's the most efficient way to calculate the 7,000th Fibonacci number directly, is to like successively square this matrix and use this little squaring trick. Great one.
Successive ratios of Fibonacci numbers approximate the golden ratio.
And if you look at ratios between successive terms, you get closer and closer to the golden ratio. Always a crowd favorite. In fact, it's the one I was counting on hearing because that's where we're going. And indeed, this is a fact. And I think we probably even know why it's true. We're a small enough group that maybe discussing can just like happen in the form of moving like to here. So we're going to try to explain to ourselves why does the golden ratio show up? How is it, and how is that implied by the recursion? So what's the next? If you give me the first step, I'll do the rest.
Limit of fn plus 1 over f.
Okay, which means you've mentally done an algebraic step here, right? Which is to, like, I don't see fn plus 1 over f anywhere, but of course we can make it appear by dividing through by. Now, one of these 3 terms is more advantageous than the others. Fn, let's divide through by Fn. We get this. We let R be the ratio between successive terms. We throw an R there and an R there. And 1 equals 0. Bummer. Well, I guess lunchtime came early today.
No, it should be 1 over r.
oh, whoops, this is the ratio right here. Of course, it's upside down. And so it's actually 1 over r right there. And then we get a quadratic equation, which, well, technically has 2 roots. We'll talk about that later. There's the one. It's kind of fun sometimes with my middle school audience to try to pull fast ones on them and see if anyone objects. This is an example of that. Because actually, not only, there are 2 fast ones. Not only does that quadratic have 2 roots, but you've already observed, it's not, like, we can't actually just write r here. These aren't the same number. We can't put r in both places or 1 over r. You have to bring in this idea of a limit, which the middle schoolers, like, this is a big idea for them. But a few of them caught on when I was giving this talk. This is something from earlier this summer that I did with an auditorium full of 120 11 through 14-year-olds, and we had a great time with it. But we bring in this limit, right? R is this ratio and the limit, and then we reach this equation. And so the golden ratio is the solution. It satisfies this, or multiplying through by phi. This is how we'll use it later. Phi squared is phi plus 1. By the way, how do we interpret the other root of the equation? Let me back up a little bit. This is something that would be, I'm looking for my sequence here. There's another root to that equation. Where does that appear?
It's 1 over.
It's right. It's the ratio as you go out to infinity, and there's another limiting ratio, and it's the ratio of terms as you go out that way. And now we can see why a negative appears. It's really there. It was there all along. Okay, that's worth. So away we go. We have our ratio, and we have our little phi fact. So that's in play, and there's nothing about the Fibonacci numbers that we needed to make this argument run. The same thing's true of any other a Fibonacci sequence, as we can see here. Here's the one we saw earlier. If we compute a few ratios between successive terms, sure enough, it's homing on 1.618, just like it's supposed to. Yeah.
Is there a sequence for which this converges fastest in some sense?
Oh, that's a
Is it the original one?
great question. I would guess so.
I'm putting a guess that the classic Fibonacci sequence either converges fastest or slowest. I mean, I haven't thought about it enough to figure out which one.
I think it converges fastest because if you look at the continued fraction for the golden ratio, that gives you Fibonacci numbers as well. So I would.
That makes sense to me too. The question by the way, is the Fibonacci sequence the one for which these ratios converge to the golden ratio most quickly in some sense? And the consensus is, yeah, probably so. To summarize the discussion, that seems quite reasonable. Okay, so we've got these limiting ratios. This suggests quite naturally, if we've got a ratio that's approximately phi, then kind of how close does our larger number come to phi times the smaller number? And I claim that this is not obvious what kind of values will come up as we check successive ratios. The numbers get bigger, but the ratio gets better. There's like this tension. And so what will happen to this difference? And so we're going to do some calculations. This is our sequence here that started 2, 7. And I went ahead and calculated all of these delta values. Just to recall, let's make sure we know where this one comes from. I've taken the next number and subtracted phi times the number in that row. So this number here should be 16 minus 9 times the golden ratio. That's where the 1.438 comes. This number here is what happens if I take 9 minus 7 times the golden ratio. I'm computing those differences. Now this time I really do want to give you a minute. I want to pause there's some data. What seems to be going on with these little delta values? Because we're starting to get into the heart of what is going to allow us to pinpoint a middle term. So this is a good thing to pause on. You should tell the person next to you what's going through your head. 30 seconds.
It seems like 9 is where like the magnitude is less than.
Or it like flips over. Yeah, it like makes that. Yeah, from bigger than 1.
I wonder if it's like exponential. It seems like it's getting like slower, like as it's decreasing.
Ooh,
It doesn't seem like
means it's time to keep moving.
right 0. The absolute value is
Yeah.
But I also want to know what's going on further to the left.
So I'll summarize some of what I can hear. Obviously, numbers getting smaller, alternating in sign. Maybe got some inkling that it's exponentially decreased, that there's a common ratio, in other words. Are we willing to make any further speculation on what else we can say about the ratio is?
No, the ratio looks like it's approximately phi. Or negative phi, rather.
Oh, right. So it does seem to be like more like 60% as big, roughly, and maybe that's 0.618, 1 over the golden ratio.
I was dividing them previous over next one. So if you do it that way around, you get
Yep.
negative 0.6.
So what we have is that each successive delta value is negative 1 over phi times the previous one. At least that's numerically what we're observing. And this is a pleasantly non-trivial but non-complicated thing to really nail, so we're going to do it. Let's see, what should happen if we like work on simplifying that expression? We're hoping to get 0. I saw a few like goose eggs around. Right, if that's 0, then we've proven it. So I'm going to set this up for us. There's delta n plus 1. We take a Fibonacci number minus phi times that. The same here. We take one of our Fibonacci numbers minus phi times the previous one. And what next? Probably like let's see how the algebraic intuition goes. What seems like a likely next step? If you tell me what to do, I'll do it. We're definitely going to multiply the phi through. I'll hold off on that for one step. I probably won't. I won't get any limits going here. That's exactly what I'll do. I'll turn gn plus 2 into that, which will allow us to like it's going to allow some combination to happen. Now, distribute and like collect. So there's the wow. What just happened? Oh, you know what? No, what happened there?
Distributed and canceled.
Yeah, we distributed, and then there's a phi gn, right there, phi gn, and then minus phi gn. So those went away. That brings us to here. Now, clearly, we'll combine all of these terms, and that's going to be 0 because golden ratio.
You even said that we should remember this.
I did even say that. That's it turned out it came in.
I was going to say, like, distribute and exploit the fact that phi squared is phi plus 1.
You saw it coming. Bingo. Okay, so it really is the case that these delta values change sign and decrease exponentially by a factor of phi. Yay. Now think back to, remember that sample sequence that I threw on the board where it was like asking about with the decimals and trying to find the middle term? How is that going to translate to this setting? That general idea. And maybe you can even point to one of these terms, like where should we look? Do you suppose?
The 1.4 to 0.8.
So, like, there are several reasons to look at this. Partly, I told us earlier the middle term was 9. So that's a good bet. But also, like, what about this delta value recommends itself to us? It's right. Somehow the middle is 1. If we have an exponentially decreasing, it wasn't powers of 2, but now it's powers of phi. The sign change is a wrinkle. We have to figure out what to do with that. But basic principle that we're going with is go with the, like we've got this sequence of values. They alternate sign, and they get smaller and smaller by a ratio of phi. So can you fill in these blanks? What's the range that we're guaranteed to be able to hit if we're trying to stay, like pick the one that's closest to 1? And I'm going to go ahead and steer us towards taking a positive value. I'm not interested in the negative value. That's a whole discussion by itself, and I'll circumvent it by fiat. With a pH, yes, exactly. What should I use for my bounds?
I was just going to say 1 over phi and phi there.
That's what I would say also. Now, you get to go down by a factor of phi each time, so it would seem that this range would allow 2 consecutive delta values to occur, but one of them will be negative, so we ignore that one. If we're looking for something close to 1, then we're going to be able to find exactly one such value in that range. And that's now this has a slightly arbitrary feeling to it, like you're leading us down a garden path. But you're also suspending disbelief, or at least willing to grant me willing to walk with me a certain, and if at some point I can produce something beautiful that arises because we're agreeing on these definitions, then you'll invite me back someday. But for now, it's this. There's some suspense. All right, let's see what happens. So here's the deal. If I have a Fibonacci sequence, I go to some term. Right? This is how I check. Is this term the middle? Well, I use the next term. I compute this difference. If it happens to be just right, meaning it's close to 1, then that's the number I'm after. And we've convinced ourselves that there's only one term in any given sequence that matches that description. And here's our definition, which we definitely need to actually try out. But there's the recipe. And if we apply it, well, here is a sequence that we haven't thought of before. So you can't just say it's 9. And what does your numeric, which ratio looks like it's just getting to being pretty good approximation for phi without being too good? If you had to, with your newly fine-tuned spot the middle term intuition, it's 5 and 6 seem too off, right? 6 and 11 maybe that's about right. 11 and 17. It's going to be a slightly tough call between like there and there. Well, here is, turns out, yeah. Let's see. It was right in that part of the sequence. Well, it was, yeah. But let's actually see the numbers. Here are those ratios. And lo and behold, the one that's closest to 1, it's pretty clearly, yeah, it's the only candidate. It's between 0.618 and 1.618. Yay, so we've spotted a middle term. Okay, so here's some for you to try. And this takes a little, this looks hard, but it's not. You can do it. Compute a few delta values. You won't have to try many, and you'll find something that works. Okay, I'm going to do one that doesn't work, and then you'll correct me and tell me the one that does work. I'm going to check and see if 2 is the middle. So what I'll do is I'll take the next term, 3, and I'll subtract 2 times the golden ratio. So that's like subtracting about 3.2. That's no good. That gives me a negative number.
Is it literally that first one to the right of the 0?
So now we'll try the 0. So we'll do 1 minus 0 times the golden ratio, which is 1. So that is bang on 1. This is actually the sequence, the one sequence for which it's possible to hit 1 on the nose. Mostly we have to be content for being pretty close. So that's kind of satisfying. It's like if I had given us this as our first example and said which number should be the middle, you would have really fought for 0. And so this is reassuring that this roundabout path we take, it does bring us to 0 as the middle. Okay, but look at what happens with twice the Fibonacci sequence. I'm going to convince us it's not that 2, or sorry, it's not 0 again. Because this time, 2 minus 0 times the golden ratio is 2. It's out of our range. It's out of the 0.618 to 1.618. So you'll have to look elsewhere. I'll give you a, let me give everyone 10, 20 seconds just to try just one spot. See what happens. Okay, with fingers, tell me which number did you vote for? I'm seeing a lot of 2s, which is nice, but which of these 2s is it? It's this 2, yes. And indeed, 4 minus twice the golden ratio is like about, let's see, about 0.8. So it's within our 0.6 to 1.6 range. Sure enough, that is our winner, that second 2 there. Here's a lovely Fibonacci sequence. And okay, that was a joke. That is not actually a Fibonacci sequence, but this one is. You can see why, like, some of us wind up in these middle school programs, because just and we need a middle term. If someone will guess, I'll run the calculation. You're going to guess which? The 5? Okay, let's try the 5. So I take 9 minus 5. So 5 times the golden ratio is about 8. Handy. 9 minus 8 is going to be right around 1. It looks like a winner. And sure enough, 5 it is. Last one, here are the Lucas numbers. And fittingly, if this is the sequence most closely associated with the Fibonacci numbers, then what ought the middle term to be? It ought to be like we feel like if there's any justice in the world, it should be that 1. And so we'll do 3 minus 1 times the golden ratio, that's 1.4. It's in our range. So indeed, it's 1. Okay, brilliant.
I have a question.
Yes, we should have questions right now.
So, is it the case that the Lucan numbers are the one where the middle estimation is worst out of all generalized Fibonacci sequences?
What do you mean by the middle estimation?
The delta value, right? So for the actual Fibonacci
Oh,
sequence, it's
I
3%.
see.
For the second one, it's like 0.8.
Let's see. So 3 minus 1 times the golden ratio is about 1.4. I think we must be able to do better than
I wonder if it's
that.
worse than that.
Or, right. I'm imagining you must be able to get something where that delta value is 1.5, or even on a really bad day 1.6. I'm assuming that these delta values.
I don't know if the bounds are type specific.
Yep. One thought. So.
Write the sequence by picking that as a difference, as a generating thing. Yeah, like you get to
Right.
generate,
Yeah. So you find some
just pick 2 numbers with that ratio.
whose ratio is 1.5, like 7 and.
Yeah, but how do you know that that's actually the middle?
Or
then? It's possible that
3
your
and
middle
2.
is now shifted somewhere else.
No, because there's only one value within the bounds, right? So as long as you
Right. If you build it so that there's a delta value of 1.5, then it will be the single delta value within our range. Yeah. Exactly. So we could build. Sure. We could build. Okay. This. Actually, I'd like to generate at least one more question. So we have. You give me a Fibonacci sequence, and I can tell you the middle number. There's something that there's this burning question that we need to ask and answer, and that is.
What does it mean? I don't know.
You're like, so.
What does it do for me?
These are okay. Come back.
Tell me anything about the sequence.
So here's sequence number 5. Ta-da! I can catalog Fibonacci sequences. Well, except can I though? Because what's the question that we need to ask?
If you give me 2 numbers, what's the middle of the Fibonacci sequence they generate?
Oh, like is there some sort of shortcut in a way? Like if I have my initial 2 numbers, can I what's the more direct route? Right. Could I have 2 different Fibonacci? Is there another Fibonacci sequence number 5, for instance? And it feels kind of unclear. Seems they're likely, surely there's another one, but wouldn't it be cool if there weren't? You're oh. So let's actually, we'll tackle all those questions in this form. Let's take a look. Is there a Fibonacci sequence number 7? And if so, are there several of them? Survey says, well, you can just, it sounds like we're going with yes. How would we build, so this idea of building a sequence that has a certain characteristic, what would we need to have happen in order for a middle term to be 7?
We need the next term to be somewhere between 7 feet plus 8 feet.
Right, we'd need the next term to work out so that this delta value gives us something in our range. Okay, let's actually write that down. Here's our next term. We would need that difference, that delta value to be in our range. So I'm just doing exactly what you said. And we need to solve for h. Well, we add 7 feet everywhere. But maybe you already saw this coming. You're like, oh, the bounds here on my inequality, they're exactly 1 apart. So whatever math I do, I'm going to wind up with an interval where I'm looking for an integer in an interval of length 1. So yeah, there's going to be a Fibonacci sequence number 7, and there won't be 2 of them. Which makes us, that makes me feel good. This is, by the way, this whole idea is based on original research that has appeared in the Fibonacci Quarterly. This was not just dreamt up It wasn't like I sat down and thought, what should we do to entertain a bunch of middle school kids for an hour? It was like, let's do good math. And then, now, how could this perhaps be made accessible to a particular audience? But it's still, like, I love this stuff. So we get, we do, in fact, have a next term. If we generate a sequence with the 7, 12, then we're golden. There it is, with the 7 in bold as the middle term. And right, but surely, so same argument should apply, right? We need a next term, h, and there should be just one. Next term, h, would have to satisfy this sort of inequality. And again, it's going to be, we're looking for an h in an interval of length 1. It'll involve negative numbers, but that doesn't matter. And that leads to this natural result here. And we get all the Fibonacci sequences out there can be, they're countably many. There's a way to catalog them. There's the 7th one, the 0th one, and math is nice, and life is good, and there's a wrinkle. Yeah.
So is this unique for non-integer k? I'm going to put in a guess for now.
Oh, it's if we expand our sort of our realm of Fibonacci sequences to include all like real valued sequences.
Take a pair of real numbers, generate that one.
I have I haven't actually pursued that at all.
Okay.
And maybe I won't speculate right here what happens, other than the nice interplay between integers and intervals of length 1 would no longer, of course, like kick in the same way. But there's a wrinkle, and also there's something we need to see. So this talk is incomplete because I've sort of misled you on one point, and I also haven't delivered the goods in terms of what, like, to answer Sophie's question of what does this do for me? So, just kidding. There's more, and it has to do with this sequence. If you didn't like -1 before, you will be even less of a fan of it after today. Because let's run our little program. We're looking for a next term. The delta value should be in this range. And out comes this. It's the one occasion when we hit this ambiguity. You'll notice, I'm sure the analysts in the room have been secretly looking down on the slides here, because I haven't been really paying attention to whether this is a less than or a less than or equal to. And that's fair, and here's where it actually matters. So it turns out you are right. What's to be done? Well, you're like, we could allow them both. We could like allow neither of them. We could somehow choose one or the other. Let me show you where this leads. And where the discuss part we'll gloss over. The first thing you notice is whether we take -1 to be the next value, like this, or 0 to be the next term after the -1, like that, we actually get the same sequence either way. So that's a small relief. Sequence number -1 is unambiguous. But where the middle is still up for grabs. Which -1 is the middle? I claim math has an answer to this, that we don't have to sort of choose one arbitrarily. And it's a little bit, but it's a little bit non-trivial to tease out what math prefers in this case. So let's do this. I'm listing all of my Fibonacci sequences. This is what you wanted to see earlier. Like when we line them all up in all their splendor, they're all like, I'm ordering them by middle term. And the question is, for this sequence right here, the sequence -1, should I use this negative one in the central column, or should I scoot that sequence to the left and use the second negative one as a middle term instead? So there's this version. Like, does it somehow slot into the whole big picture correctly this way or that way? And it's, again, not, like, knowing, that's a lot of numbers on the screen.
So, dumb question, why not the third way? Because if you do it the third way, it looks like you wind up with Fibonacci sequences on the columns, too.
Oh, this can't be the middle term because if you do, the delta value here is not in the range. It's negative, I think. Yeah, it must be negative. So, so unfortunately, that's off the table. Unless we want to bend the rules. You always, right? We're mathematicians in the back of our minds. We're like, shall we? Maybe this is the right place. Anyway, I'm going to direct your attention to a part of this diagram because it took me a while to tumble to this, and it's really kind of unexpected. Actually, it's sort of sensational. It really is mind-blowing. Okay, so I'm going to go to that big grid, and we're going to toss a little double bar in here just to focus your attention on this particular right half. I'm looking at the numbers over here, and I claim something happens there. Now notice in this. So there's the first array. Regardless of what we do with the bottom row, the positive numbers all stay the same. So maybe I'll even focus your attention on the upper right quadrant. It's like, that's a lot of numbers. Every number appears once. There's the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 is there, 16, 17 is up there, 18. Every positive integer appears exactly once. It's like, we've heard of complementary sequences. When you take two sequences and you get every integer exactly once, and there's some fun stuff. This is like it's like infinitely many sequences that are complementary. Which, of course, we immediately turn our attention to the bottom quadrant. We're like, okay, what's going on down here? And it's not symmetrical. It's not the same thing with negatives. That's interesting. It's like a slightly different way of all the numbers appearing. We have the repeat -1, so that bothers us. But then after that, things are good. 2, 3, 4, 5, 6, 7. Come back. And so let's compare this version. This is a version that has 2 -1s and no 0. But otherwise, every integer appears to the right of the double bars. In the other version of the array, this is how I felt when I first saw this. I mean, I remember the exact place. I was sitting at that table in that room when I lived in that address. It was like, it's etched on my mind. Let's see. Oh, I guess, okay, so I was imagining I set a slide up differently, but I didn't. But so imagine that if we instead slid this bottom row to the right, and that -1 was the middle term. I lied. Imagine we slide this to the left, and this -1 is actually the middle term, which means that the -2 starts here. Then we're missing zeros and -1s, which seems like a slightly less desirable state of affairs than having a -1 twice but no 0. But maybe there's some room for debate there. there's a small other, if you're familiar with Beatty sequences, it turns out this is the Beatty sequence for the golden ratio. This is on multiples of the golden ratio, the floor of them. No, it's the floor. It's like the greatest integer, not larger than them. So there's reason to like this column here sitting next to that column. And for a couple of reasons, this is the right way to picture sequence number -1. And at this point, it's sort of a choose your own adventure. Meaning, we've reached a point in all of this where you've seen the big reveal has occurred, and we've spent a lot of with middle school students, we would be done. And so I'm going to actually maybe ask you, there's a way to understand why that happens. That would take 5 more minutes to just let it wash over us and 10 more minutes to really drill down. I'm definitely going to be sharing these slides. You can go back and look at this on your own time. What should we do now? I'm really perfectly content with any of the above options, and I'm not even sure how we make this decision. What's that?
I'd like to understand.
We'll go at least trying to see the ideas. You've got them mostly already in mind. All right, I'm going 5 more minutes, and then we'll. And then, like I said, you can go and look at this later to your heart's content. Okay, so it's another fake ending, which, the kids even wanted to see the slide after this, so I was ready for them. I was like, nope, that's it. Okay, but it wasn't. So we've got our little delta values. And when we're at the middle term of a sequence, we know that value is between 1 over phi and phi. It's between 0.618 and 1.618. But at different places in the array, this value changes. So what I'm saying is, right here, the delta values for these positions within the sequence is within our little range, 1 over phi to phi. How is that value going to change as we move one column to the right? How do successive delta values differ from the previous ones? I'm asking you to remember. So it's -1 over phi times as large. So we have a new little range. It's going to be between two negative numbers, and it'll be slightly smaller. So let's do that here. Let's see that, because it's not doing algebra in our heads. So I'm going to divide this by -1 over phi. So there'll be a -1 over phi squared. I'll divide that by -phi, and I'll get a -1, and all the signs will reverse order. And that will bring us to here. Right? That gave us the -1. That gave us the -1 over phi squared. All those values down that next essential column will have those delta values. Okay. Yeah. Oh, that's a good question. Ooh. When did? Oh, you know what? I put that in because we chose the. It had to do with the -1. Which -1 we chose to be the middle.
Okay, so you did make this choice, right?
It's the choice, right? I made that choice, and we split the. We settled the matter via which position we. That's good. So analyst, I'm assuming, right? Or detail oriented. Perfect. So we have this, and then we can keep that going. The column after that, this is now, we've just entered past the double bars now in our big picture. Column after that will satisfy divide by -phi again, and we'll get to here. So numbers in the first column that we care about, past the double bars, all the delta values satisfy this this inequality. They fall in that range. The ranges are starting to get smaller. And then we can keep going. The next column after that, divide by negative phi, divide by negative phi. Each column gives delta values within a certain range. Now let's put all those ranges together. So there's the range for delta values in the first column past the double bars. And then here's the range for the column after that. Those were negative numbers. After that, we get here. After that, we get here. And they all pack in. You can kind of see that in total, we get, well, let's see. We get, what can we say about this set of values? It looks like a unit interval, but there's a tiny wrinkle, which turns out to be important. 0 is not part of this set. But it does have unit length. So there's the exact. So if I take any number in the right-hand part of the array, and compute a delta value for it, I'm going to be in this range. The inequality signs do work out this way because of the reversal of the order. And this interval does have length 1. Pretty straightforward to check. Run our little calculation, and good old phi fact kicks in once more. Okay, so let's suppose I'm looking for the number, looking for a particular integer off to the right. It would need to have a next term that gave me a delta value that was somewhere in this range, because it was one of those individual little intervals. And that's an interval of length 1. So we can go through this one more example, but you've seen this idea already, right? If we wanted to look for 1776 in the array, well, we'd need an h value for which this occurred, and that leads to looking for an h value in that range. And so I can even tell you the number after 1776 must be 2873. Did I do that right? No, 2874. That, like, wherever it is out there, it's going to be right next to 2874. And so I can even tell you which sequence it's in by working backwards. So there's, and of course, there's only one solution in each case. How often does -1 appear? Now we get to this kind of, like, this is the one case where we hit both endpoints. And so putting the little equal sign where I did leads to that. And 0 doesn't appear at all because we're looking for an h value in an interval, but it hits that one value that's not at our disposal. And so that's the whole story. And that's a squircle because that's the logo for Proof School. So thank you very much for your attention. Amazing. Oh, even the secret ones. I'll toss them in for a small fee. Yeah.
All right, let's give one more round of applause.
Thank you.
And a round of applause to the audience.
Yeah, really, honestly, thank you. This was obviously designed to be a very, very much a joint effort. And that only works if you're willing to come along. So thank you.